Reasons we may never know, potential is realized. The event, the Big Bang, occurs with unimaginable force. Nothingness is replaced with blinding, swirling energy. This is the universe, just 1/1000th of a second after its birth. Here, deep inside the Big Bang, all the way down to the molecular level, there is a searing cauldron of radiation. A soup of nuclear matter, so hot that as atoms and other building blocks of matter try to form, they are quickly blown apart. Now, just a microsecond after the Big Bang, if we could view the expanding universe from a vantage point light years away, we'd observe in these blue ripples the entirety of space forming, rippling outward from the Big Bang in waves of energy. Within a millionth of a second, the universe is the size of our solar system and as dense as the core of the sun. It's doubling in size, all within a blink of an eye. Its outer border is creating space as it goes, because just beyond these ripples of matter, there is no space. The outer edges are bending and folding as the universe expands. Scientists don't all agree on what the universe is actually expanding into. Out here, time and space itself do not exist, so we are depicting the undepictable. But if we could see this expansion just moments after the Big Bang, this is one theory of what it might look like. This is the chaotic creation of space and time itself. At the edges, we are looking at the fabric of our universe, finding its way from nothingness to everything. And while space and time are being created at the edges, back down here at the molecular level, we would observe a sea of particles as temperatures begin to drop to about 1 billion degrees. If we were to examine more closely, we could see the nuclei of hydrogen and helium. The universe is cooling just enough for atoms to form, and they do. Trying to see the universe at this stage is impossible. As the minutes turn to hours, the hours to years, and years to centuries, the universe is still a hot mass of plasma and radiation. But the process of cooling continued. And as it cooled and expanded over hundreds of thousands of years, it became less dense, like rocks breaking apart. This era, before the birth of stars and galaxies, lasted for millions of years. Before we see how stars were born and space became a brighter place, let's take a look at how our universe actually expands. In all the dramatic evolution of the universe, the one constant has been its continual expansion. Imagine a three-dimensional balloon slowly inflating. As the balloon expands, the stars and galaxies move further apart, away from the Big Bang at the center. The size of space grows larger, but the stars and galaxies remain the same size. The universe we know is still expanding, and although there was nothing that could match the power of the Big Bang, there are still forces in the universe that simply defy our imagination and are every bit as wondrous as the beginning of time and space. For millions and millions of years after the Big Bang, there were still no stars in the universe. But the universe was rehearsing ways to make them. The seeds of these early stars were planted in immense hydrogen clouds that became so dense they ignited nuclear hydrogen bomb-like explosions. Luminous, short-lived behemoths were born, 100 times larger than our sun, 1,000,000 times brighter. And even though these very first protostars would burn for a very short time, about 1,000,000 years, the universe was forever changed. The cosmic dark ages were over. Everything we can see or touch today was born from these early stars. This is how our own solar system began to form 4.6 billion years ago. From the wreckage of a supernova, interstellar gas and dust began to cluster together in a molecular cloud known as the solar nebula. As this cloud collapsed, its center became a hot, swirling nuclear fire. Our sun was born. Looking at our solar system more than 4 billion years ago, strong stellar winds expelled gas, dust, and debris from this new star. Clumps of molecular matter formed and orbited around it. These were the seeds for planet formation, the blueprints for Earth and our other planets. And as they filled the early solar system, they coalesced into larger and larger formations until they became boulders so big they eventually had their own gravitational fields. These inner rocky terrestrial bodies were all orbiting at roughly the same speed around the sun, making it easier for them to coalesce. This process is called accretion, and it's how our solar system began to take shape. Not all bodies found a place in orbit around the sun. Some icy rocks were flung out of orbit and became comets, destined to wander the reaches of the solar system. But after 2 million years circling around our sun, the larger bodies eventually became early planets, and they began to claim their own space. Coming together in a protoplanetary disk in a violent corner of space. Once these early planets became large enough, gravity and pressure shaped them into spheres. This shape is a constant in our universe. From planets and stars, to molecules and cells too small for the eye to see. They all perform a similar cosmic dance. Whether it's electrons orbiting a nucleus, our moon orbiting the Earth more than 200,000 miles away, or neighboring and distant planets orbiting the sun. They all perform the dance of the spheres. After a fiery and cataclysmic start, our solar system today, around 4.6 billion years old, has reached an equilibrium. A perfect harmony of the spheres around our sun. But over time, nothing in space remains constant. 200 million years after the Big Bang, the universe looked a lot different than it does today. There were no galaxies yet, or planets. Just clouds of gas and some early unstable stars called protostars. Massive bodies of heat just burning through their hydrogen. And when that hydrogen was gone, they collapsed. Behold the birth of a supernova. Its light capable of outshining an entire galaxy. These supernova blasts did more than light up the universe. They also sent elements like carbon and oxygen, which had never existed before, into surrounding gas clouds, changing their chemistry. Inside these clouds, carbon and oxygen began to burn, causing massive chemical reactions. From all the chaos, a second generation of stars was created. Stars that looked and behaved more like our own sun. They often collected in dwarf galaxies. This dense ball of dust and gas is a dwarf galaxy known as a starburst, one of the oldest in the universe. But how did galaxies form? Galaxies like our own Milky Way. As large as galaxies are, it's the forces at the center that drive them. No stars live forever, but some are reincarnated, leaving a neutron star in its wake. Surrounding many neutron stars are disks of debris, like those around Saturn. These extremely dense stars are small, just 12 miles in diameter, smaller than New York City. Yet they have a great deal more mass than our sun. Their enormous gravitational fields actually bend light as it passes. Some neutron stars have gravity that's 100 billion times stronger than what we experience on Earth. How do you explain the force of that kind of gravity? Imagine it this way. Matter is packed so tight on a neutron star that a sugar cube of material, if you could find a spoon strong enough to hold it, would weigh the same as Mount Everest, about 1 billion pounds. Think about that. On a neutron star, the crush of gravity is so strong, it would be like condensing the highest mountain on Earth down to a spoonful of sugar. Some neutron stars have magnetic and rotational axes that are misaligned, and they spin wildly in space with brilliant beams of light sweeping the skies around them. It wasn't until 1967 when scientists observed a flashing star in distant space